Okay. Sorry, give me a second. Pull up my camera here. Okay. All right. Uh, okay. So this is officially my last homework. At this point, I have not submitted it yet, but I've already completed process dynamics. So, finishing up homework five for separations, and what we'll be doing today is part B. My partner Chibudom already finished part A, that is done. So we're gonna go ahead and start. We'll be deriving the mesh distillation equations for the first stage below the condenser, the reboiler, and all stages in between, assuming any stages can be the feed stage. So we'll kind of end it off with that like total feed stage and show how that's done. But before I kind of go ahead and start with this, I'm gonna go ahead and draw out a little schematic of a distillation column, or at least a schematic as close as I can get, but all right. So this is our distillation column. We're gonna go out and draw those kind of tray lines right here. Okay, and with this, we know we have that total feed coming in, as well as the composition of the feeds right here, right? So we also want to make sure in this distillation column we have our reboiler and condenser. So let's say we have some vapor coming up here. We have our condenser right here, and we have our distillate leaving here. Okay, so we can also put an arrow there. This is essentially our condenser, and then we have our reflux ratio here, and we also have our reboiler here, which will be kind of deriving. So let's do it like this. Come back here. Okay, so not the best schematic, but somewhat kind of what we want to see. I usually put the problem statement inside, but I kind of forgot to do that at this point. I already went ahead and read it, and I'll make sure to kind of put the problem statements for the other parts. But for the derivations, let me just go ahead and read it again. We're deriving this distillation equations for the first stage below the condenser, reboiler, and all the stages in between. So before we kind of get into it, I do want to mention kind of the things that we're going to be looking at, right? So we're going to be looking at material balance, an equilibrium kind of balance. We're going to be looking at a summation of the mesh equations, as well as a heat balance. So four things for all of our things. So the top stage, we'll have our reboiler, intermediate, condenser, total feed stage essentially. So quite a few derivations. Try to be as kind of what's the word? Well, yeah, let's just get into it. All right, so we have this little diagram here. I'm gonna go ahead and start our top stage right here. Okay. And with this top stage, I'm gonna go ahead and first start by looking at our material balance. And for material balance, we're essentially looking uh, at our liquids and we're looking at both our liquids and vapors as well as our distillate in this case. So it will be our liquid flow at stage 2 multiplied by our liquid composition at stage 2 at component I, referencing our species I in this case. And then this is going to be added to our distillate multiplied by our composition of our distillate uh, as well as our component I here, right? So this is all going to be equal to our vapor flow at stage 1 multiplied by our vapor composition at stage 1, referencing our component I here, okay? All right, so as far as our equilibrium, um, okay, so let's do let's do this. All right, we're gonna make all of these. So this is our material balance, our equilibrium. Okay. So for our equilibrium, this will so you'll see as we go through all our other ones, this is going to involve our K value essentially for all of our equilibriums. So just to keep that in mind, and for specifically our top stage, we're referencing our vapor composition and liquid compositions in this case. So it'll be our vapor composition at stage one, first component I, equal to our K value at stage one at component I multiplied by our liquid composition at stage one at component I. Okay. All right, so next we want to work on our summation of our mesh equations. Okay. So for this, essentially you'll kind of see that I think almost, but I'm pretty sure that they'll all end up equaling to one when we're referencing at stage n at species I equals one, the summation of either our liquid compositions or our vapor compositions will end up equaling one. So let's look first off, starting with our summation at species I equals one at stage n for our liquid composition at stage one for component I, and then this will equal one. All right, so now when we're looking at our vapor composition, so again, summation at stage one n at component I equals one. We're looking at our vapor composition at stage one for component I, and then this will equal one. Okay. All right, so now that we've done that, we can go ahead and move on to our um, material balance. No, sorry. We can go ahead and move on to our heat balance. So this will be the last of the four things we need to look at for each one that we're kind of deriving. So looking at our heat balance, this will obviously involve our enthalpies as well as either heat added or heat removed if we're referencing our condenser or reboiler. So in this case, we're starting off with our vapor flow at stage one multiplied by our vapor enthalpy, so it will be denoted by HV, plus our liquid flow at stage two multiplied by our liquid enthalpy, plus our heat removed or heat added by our condenser, which will be denoted as QC. And this will be all equal to our distillate multiplied by our enthalpy of our distillate. So our distillate enthalpy. Okay. So that completes our top stage. Okay, so this we'll now be looking at our reboiler. So starting with this, of course, we're going to start off with our material balance. All right, starting off with our material balance, we're going to be looking at specifically at our stages n plus one for this case, as well as our bottoms. So looking at this again, if you look back at our schematic that we drew, it's at the bottoms. So looking at this, we have our liquid flow for our bottoms multiplied by our composition of our bottoms at component I plus our vapor flow at stage n multiplied by our vapor composition at stage n at any stage n for our component I, and this is going to be equal to our liquid flow at stage n plus 1 multiplied by our liquid composition at stage n plus 1 as well as our I component species. All right, so now looking at our equilibrium. So for our equilibrium, we're going to be looking again at our K value, but we're going to be looking at our vapor composition as well as our liquid composition. I believe we did also before. So doing that, we get our vapor composition at stage n for component I equal to our K value multiply at stage n actually, sorry, at component I. And this is going to be multiplied by our vapor flow at stage n at I. No, sorry. This is going to be for our liquid composition at stage n for component I. Cool. All right, so now looking at our summation. So for our summation, again, this is going to be equal to 1. And in this case, it's going to involve our stage n plus 1 essentially. So um, again, I equals 1 at stage n at liquid composition, our liquid composition at stage n plus 1 as well as our component I. And this is going to be equal to 1. And we are also going to be looking at another summation again at I equals 1 at stage n for our liquid composition at stage n for component I, and this will as well be equal to 1. Okay, so now looking at our heat balance. So for our heat balance in this case, okay, so for our heat balance, again, we're involving our enthalpies and we're involving kind of the heat either removed or added from either a condenser or reboiler. Again, we're looking at our reboiler, so there'll be their heat added to our reboiler. So this will be our vapor flow at stage n multiplied by our vapor enthalpy plus our heat added to our reboiler. So it's going to be noted by QR equal to our liquid flow as um, liquid flow at our bottoms multiplied by our liquid enthalpy. Sorry, there you go. Okay, so now what we want to look at is essentially our intermediate stages. So it's anything kind of in between our reboiler and top stage. All right, sorry about that. So we're looking at our intermediate stages, and again, that's anything in between our top stage and our reboiler. So for our intermediate stage, so our stages for yeah, so for this we're gonna be looking initially again at our material balance, and this is gonna be somewhat longer because there's so many things involved. But this is gonna be starting with our liquid flow at stage n plus 1 multiplied by our liquid composition at stage n plus 1. Um, yeah, at stage n plus 1. Yeah, stage n plus 1 at component I, sorry. And this is going to be added to our vapor flow at stage n minus 1 multiplied by our liquid or vapor composition at stage n minus 1 at component I. And then this is going to be equal to our liquid flow at stage n multiplied by our liquid composition at stage n at component I plus our vapor flow at stage n multiplied by our vapor composition at stage n as well as component I. Let me go ahead and look at this, make sure this is right. Yep, so we have our n plus 1 stages or n minus 1 stages, and then on the right hand side is just our n stages. So that looks good. We can now do our equilibrium stages. So essentially we're looking at, again, our vapor and liquid. Okay, so our equilibrium. And for this, we're going to be looking at our vapor composition at stage n at component I equal to our K value at stage n at component I multiplied by our liquid composition at stage n for component I. Okay, so now we can go ahead and look at our summation for this. So for our summation, make sure I'm recording here. Okay. So for our summation here, I'm gonna say it every single time we go through it, but it's gonna be equal to 1, and it's always gonna involve our liquid and vapor compositions. But it always kind of just depends what stage you're looking at. Again, we're either looking at a reboiler top stage, intermediates, whatever it is, that's really what will differ specifically with our summation. Because I think, even for our material balances, I mean, we're always working with our liquid and vapor, but um, it's always a different equation because it depends on kind of what's coming into uh, this stage and leaving this stage, right? So, but the summation is quite similar. So I equals 1 at stage n for our liquid composition at stage n at component I equals 1, and then a summation at I equals 1 at stage n for our vapor composition at stage n at component I, and then this is going to equal 1 as well. All right, so to end off our intermediates, again, we're going to do our heat balance. And for our heat balance time, it's going to look a little bit more in depth, but it's going to be our vapor flow at stage n multiplied by our vapor enthalpy at stage n plus our liquid flow at stage n plus 1 multiplied by our vapor enthalpy at stage, no, sorry. I'm going to go ahead and look at my notes real quick. Okay, yeah, so this is going to be at our liquid enthalpy at stage n plus 1 plus our heat plus our Qn in this case at stage n. So this is going to be equal to our liquid flow at stage n multiplied by our liquid enthalpy at stage n plus our vapor flow at stage n minus 1 multiplied by our enthalpy at stage at our enthalpy vapor. Yeah, pretty sure that looks good. Yeah, that looks good. Okay. So what we can do now is no, we're not done. Okay, so this is gonna be at stage n minus 1. Sorry about that. Okay, so there you go. That's good. A lot better. Okay. Okay, so we can finally end this off with our feed stage, and our feed stage is essentially gonna be um kind of involving specifically of course our feed, but as well as our composition of our feeds. So it's kind of everything that's coming inside to our distillation column essentially. So with this, again, we're going to start with our material balance. And for this, we're looking at our liquid flow at stage F plus 1 multiplied by our liquid composition at F plus 1 for component I. And this is going to be added to our vapor flow at stage F minus 1. Um, Essentially, when we look at this specifically, I guess for feed, it's a little different, but F minus 1 is going to be referring to above the feed, like that stage above the feed, and then R plus 1 is going to be below. So it's a little bit tricky, but just something to keep in mind. All right, so this is going to be multiplied by our vapor composition at F minus 1 at stage I plus our total feed multiplied by our composition of our feed at component I. And then this is going to be equal to our liquid, liquid feed multiplied by our composition of our liquid composition of our feeds at component I plus our vapor flow at F multiplied by our vapor composition at F for component I. Okay, that looks good. Okay, so now we can go ahead and do our equilibrium. And for this one is essentially going to be similar to what we did for the other ones. However, instead of at stage N, we're looking I guess at stage F, or yeah. So our vapor composition at F for component I is going to be equal to our K times K for our feed at component I multiplied by our liquid composition at our component F at species I. Okay. So like I said, for summation, I'm gonna say the same thing every time. It's gonna be equal to 1. So for this case, it's going to be super similar to our others. We're looking at a liquid composition, we're looking at a feed composition. And I mentioned before that the only thing that's going to be different is what kind of stage we're looking at. We're looking at. So essentially this is going to be at our feed stage in this case because we're looking at our feed. All right, so this is going to be a summation of species I equals 1 at stage n for our liquid composition at stage F for component I, and that's going to be equal to 1. So for our second summation, I equals 1 at stage n, we're looking at our vapor composition at stage F for component I equal to 1 as well. Okay, so last but least, last one, not last but not least, is going to be our heat balance for our feed. And for this, it's going to be our vapor flow at stage F multiplied by our vapor enthalpy at stage F plus our liquid flow at stage F plus 1 multiplied by our liquid enthalpy at stage F plus 1 plus our heat added to or from our feed. And then this is going to be equal to our liquid flow at stage F multiplied by our liquid enthalpy at stage F plus our vapor flow at stage F minus 1 at stage F minus 1 multiplied by our vapor, our vapor enthalpy at stage F minus 1. Okay, all right, so that completes it. These are pretty much all of our uh derivations for our intermediates, our feed stage, our reboiler, as well as our top stage. Cool. All right, we can go ahead and I believe the next few parts are gonna be somewhat kind of combined, but not really, but I think they're all gonna be coding. So yeah, we'll get into that now. Okay, so starting the second part of homework 5 for separations, um, this will be kind of the last kind of chunk that we have to do somewhat all together, which is all going to be coded, but we'll be implementing those mesh equations that we derived in the last part and solving them using Newton's method and applying Thomas' algorithm for the linearized tri-diagonal block equations at each Newton iteration. Then we will be applying the mesh code towards the solution of a distillation column with 10 stages, including the reboiler below a total condenser for a 2 mole per second equimolar feed of ethanol and water to the 8th stage counting from the top. The feed enters at a temperature set to the average of a dew and bubble point temperature of an equimolar ethanol water mixture, assuming a uniform column pressure of 100,000 pascals with distillate flow of 1 mole per second and reflux ratio of 5. Further, assume that the distillate and reflux are at their saturated liquid temperature. We'll also be generating an XY diagram with the equilibrium curve and the vapor liquid compositions at and between the trays. So if you go here and look at my code so far, this is pretty much what we did in the previous part. Just have to change a few things such as I believe it was isopropanol, change that to ethanol. But this is what we did in the homework, was it? Finding our bubble and do temperature and pressure. I forget the homework, but the homework name number. But we're just gonna be continuing off of this. So starting out, we kind of need to define what or the number of components that we need. So that's going to be denoted by NC equal to P dot and then our molecular weight. And then this will be our size. Okay. So essentially it's using our molecular weight to find our number of components. And then we're gonna set our feed total. So we're gonna set that to 2 as it says in the problem statement. Okay. We also want to set our compositions essentially for this feed. So going to be denoting that by Z, and then this is going to be equal to an MP dot array of 0 0.5, comma 0 0.5. Okay. All right. Okay. So and we also want to set our pressure to 100 6,000 pascals. So setting our pressure that is to like uppercase P, meaning kind of our total pressure. And then we're going to be denoting this by 1 E5, so 1 times 10 to the 5. And again, this is in pascals, so I can go ahead and kind of just make you know that pascals. And then we're going to want to be, oh, whoops. Okay, we're then going to want to be setting essentially our dew temperature. So this is going to be a temperature, and this will just kind of be a blank because we don't need to put anything there per se. And then it'll be referring to our NRT pressure. So NRTL for our mixture and total pressure. Okay. So we also want to do this for our bubble temperature. And then we go back and there you go. So for our bubble temperature, this will be equal, or we also have our kind of blank thing right here, and this will be equal to our bubble temperature and our TL temperature, again, for our mixture and total pressure. Okay. So we also want to set up our feed temperature. So again, we're gonna have, oh, well, no, we won't have our blank for this, just for dew and doing bubble, but for our feed temperature, this will be equal to our bubble temperature plus our dew temperature, and then it'd be divided by 2. Okay, so then we're gonna want to go ahead and set some functions. So x and y and VF, which will be, we also want our blank one here, sorry, which will essentially be equal to our flash and our TL pressure total for our mixture and our total pressure for our feed temperature. Okay. So we also want to set our feed enthalpy. So that will be equal to our P dot vapor enthalpy. So we're gonna be denoting that like that. I was messing up practicing this by like I just assume I would look like this, but then yeah, anyways. All right, let me make sure I'm still good. Okay, we're good. So P dot HV, and then this will include our F total times our VF, right? So our VF times our Y and our feed total here. Okay. And then this will be added to our enthalpy of our liquid in this case. I believe let me go ahead and check my notes. Okay, so it will be F total. So F total times 1 times 1, yeah, times 1 minus VF, and then times X, and then our feed temperature, right? Okay, cool. So that should look good. Let's go ahead and run all of this. Hmm. Mhm. Let this all run. Okay, perfect. I was kind of worried because I'm kind of using the code that was already in our uh kind of our group class the collab the codes that you actually professor posts, and the one that I made previously, I don't know where that one went, so I kind of had to come down and use this one, which was kind of unfortunate because I kind of like the one that I made. But okay. So we also want to go ahead and set some initial parameters. So that's going to be our distillate equal to 1, our bottoms total equal to our feed total minus our distillate. And then we'll have our reflux ratio equal to 5. We'll have our NS equal to 10 and NF equal to 5? Or no, I think 8. Yeah, so I think that's good. All right. All right, so we're now going to want to set up our unknowns. So we're going to say that, kind of define it as unc, and then that's going to be equal to MP dot zeros for our number of stages. So NS, and then 2 times our number of components plus 1. Shift enter that. Okay, and then we're gonna want to go ahead and set up our liquid totals. Our liquid totals, I think, in the stripping, rectifying, our vapor totals in the stripping and rectifying. So let's go ahead and do that, and we're gonna label this as L total. So L tot underscore rec, and then this is gonna be equal to our reflux times our distillate. Okay, that's good. All right, then I'm gonna do L total for our stripping, and then this is gonna be equal to our L total rec plus our F total. Yeah, plus our F total times our or times 1 minus VF. Yeah. Okay. Paper feed. Yeah. Okay. So we want to go ahead and then do this for our uh our vapors. So we're gonna label this as V tote underscore rec. And then this is gonna just be equal to R. So it's gonna look similar. Our reflux times our distillate plus our distillate. And then for our stripping, will look like F V total underscore strip equals our V tot underscore rec minus our F total, oh, minus our F total times VF. Did I set VF too? Okay. Right. All right, I'm gonna go ahead and feel like I made some mistakes, but I'm not sure. So I'm gonna go and see if I did make any. Okay, so now we want to go ahead and set up our initial guesses for all of these. So our liquid rectifying, our liquid stripping, vapor rectifying, and vapor stripping. And then at the end, we're going to be creating a linspace function and connecting this to our bubble temperatures and dew temperatures or NROTL functions essentially. So starting with we're going to be using our unknowns. We're going to be using a lot of these. So for our first unknown, we can put a little semicolon here, nothing on the left, right? And then it'll be our NF, comma, and then another semicolon, and then our number of components. Okay. And then this is going to be equal to our L total. And then we're going to be starting with our rectifying. And then this will be multiplied by our Y, which is our vapor composition. Okay, so we just want to make sure that looks right. The total rectifying times y and f. Okay, so setting our next unknown for this one, uh we're gonna be using our NF and then using a semicolon and then putting in comma and oh sorry, there's gonna be something on the right. We're using -1, right? And then on the right side, semicolon and then number of components. Okay. And then for this one, we're going to be using our L total stripping, and we're going to be multiplying that by our liquid composition. Okay. So for our next unknown, we're moving on to our vapors. So for this one, it's going to be starting with our -1 essentially, and then putting a semicolon here, and then our number of components. And then this again will be for our actually our bottoms total. Yeah, this one will be for our bottoms total times our liquid composition. Okay. Move that from okay. Now we're gonna move on to our vapors. All right, so for our next unknown, we're setting a semicolon here, NF, and then uh NC semicolon 2 times our number of components. And then this will be equal to our V total and our rectifying times Y. And then for our next unknown, we're going to be setting up our V total and our stripping multiplying by our liquid composition. So looking at NF here, we're going to be putting, sorry, so unknown. Okay. So for our next one, we're going to be putting NF here with our semicolon and then, okay, starting to forget a little bit. Let me go ahead and pause this. Okay, yeah, so this throws me off and there's like stuff there that just kind of confuses me and it's not right. I'm like, what if I'm wrong? But yeah, so it's gonna look like this, 2 times NC, and then this will be equal to our V in our stripping section times our liquid composition X. Okay. All right, so for our last one, essentially setting up our NRTL functions. So a bracket here, semicolon, comma, -1. Go ahead and go close this. And then we'll be equaling this to MP dot length space for our bubble temperature, bubble temperature for NRTL. And then pause this. Okay, so got a little confused here, but we're gonna be opening another parenthesis here and using our Y composition and our total pressure, and then using our zero function, and then comma here. Then we're gonna be looking at our dew, so our dew temperature for NRTL, and for this one, we're gonna be looking at our X composition and our total pressure. And then we'll go ahead and put this here, and then our NS, so number of stages, and then close it. That should be good. Perfect. Hopefully I didn't make a mistake, but we'll come back to it if we did. And so we're going to go ahead and finally put all of these mesh equations and our unknown functions that we kind of compiled, and we're going to put it into essentially a bunch of different functions. And within this, we're going to be defining quite a lot of few things and setting a lot of different parameters. So going ahead and starting with this, we're going to be defining a few different stages, three, I think, in total. So we're going to go ahead and start with the first. So we're defining stage one. And then this is going to be for three different vectors essentially. So vector, and we're going to call it, and then vector two, and then our reflux temperature. Okay. All right. So we'll then want to kind of set two different variables for our temperature. So T and T2. And then this will be equal to our vector. And it's going to be grabbing -1. And then we're going to be setting this for our vector 2 as well. And then this is going to be grabbing -1 as well. Okay. So we're then going to want to set parameters for our liquid and vapor. And this is going to be equal to, but we're going to be splitting this. So we're going to be using the JMP function. So splitting this, we get our vector, first vector essentially, which will be grabbing a semicolon -1. So nothing on the left, but we'll have -1 on the right. Correct, yeah. Okay, and then comma 2. And then we're going to want to be setting L2 and V2. And then again, we're going to be using our split function. And for this, we're going to be using our vector 2 and then doing the same thing here. So -1, comma 2. Okay. So then we're going to want to set our kind of new liquid compositions and vapor compositions. So starting with X, denoting this by X, this is going to be equal to our liquid divided by, and then we're going to use our sum function. So JMP dot sum for our liquid. And then for our vapor, so Y is going to be equal to our vapor divided by then our sum function. and then our vapor here. Okay, I'm gonna go ahead and pause this. Okay, so we can actually go ahead and actually set up our mesh equations now that we have these variables set here. So starting with our material balance, essentially doing what we did, kind of inner derivation, and this is going to be equal to V2 that we just set plus our reflux times our, oh, sorry, plus our reflux times our distillate, correct? Times our Y, so our vapor composition essentially subtracting by our vapor and subtracting our liquid and close this out and divide it by our F total. Okay, all right, looks good. All right, we're now going to set up essentially our equilibrium equation. That's going to be denoted as EQ in this case. And it's going to be equal to X times our NRLTL gamma function. So NRLTL underscore gamma for our functions of X and T. And then this will be multiplied by our P, our P dot P vap, yeah, P dot P vap for our function of T. And then we'll go ahead and subtract our vapor composition here. Okay. Now setting up our energy balance essentially, and we'll be denoting this as EB. And this is going to be equal to I believe our total pressure. No, I don't think it is. Hold up. Okay, so this is our vapor enthalpy. So H P dot HV is going to be denoted by, and then we're going to be using our second vapor flow as well as our second temperature that we defined earlier. And then we're going to be adding this to our liquid enthalpy. So P dot HL. And then in our parentheses here, we're going to be multiplying our reflux ratio times our distillate times our vapor composition, and then setting our reflux temperature here. So, okay, I think that looks good. And then we're going to be subtracting our vapor enthalpy, so P dot HV for our vapor as well as our temperature. And then we're going to be subtracting, oh, yeah, I think there's still a, okay, so we're going to be subtracting our liquid enthalpy, so HL for our liquid and our temperature. So just L and T, and then gonna be dividing this by our enthalpy feed. Did I? Let me make sure I was here. I denoted this feed H. Okay, feed H. Okay, I think that looks good. Okay, so last thing we want to go ahead and return this. So turning this, we get JNP R underscore for all of these three essentially mesh equations. So our mass balance, our equilibrium equation, and our energy balance. Let's go ahead and put, okay. Okay, so I believe that looks good. I'm gonna go ahead and double check that before I do the other two stages because they do look a lot similar, so I don't want to mess all three up. All right, so continuing off from where we left off, we have to go ahead and define some other stages. Our original stage and our end stage, and it's gonna involve different functions. Here we had vector, vector two, and reflux T. So it's gonna involve many different things, but we'll be setting up the same mass balance, equilibrium, um, and energy balance for another one. And for another one, we're gonna have a second mass balance. So let's go ahead and get into it. So for the second one, we're going to go ahead and define our stage. And for this one, it's going to be vector one, vector, vector two, and F and FH. Right. And then we're going to go ahead and initialize some of our t's. For this one, last one we did t and t2. For this one, we're doing t1, sorry, t and t2. And then this will equal vector 1 for our net for grabbing our -1 function. And then vector grabbing our -1 function. And vector 2 grabbing our -1 function. Okay. So we can go ahead and define some of our liquid and vapors. For this one, because we brought in our vector 1, we're going to be looking at L1 and V1, V1, and then this will be equal to J and P dot split. We're splitting this function here for vector 1, and then we can go ahead and grab our -1, comma 2. Okay. So we're going to go ahead and do this for our L and V. But because this one's going to be the same as the other one, I'm just going to go ahead and grab this one. Or actually, it's going to be the same for these two. So we just need to go ahead and grab these two. Go ahead and copy and paste them. Okay. From this point, we can go ahead and define our X's and Y's. However, again, it's going to be the same. So let's just go ahead and grab these. It's going to start looking different once we start our mass balances, essentially. Okay. All right, now starting our mass balance, this will be equal to F plus V2 plus L1 minus V minus L. Okay. And then this will be divided by our total feed. Okay, so for our equilibrium equation, this will be equal to X times P dot NRLT gamma, so our gamma function essentially for X and T, big T, so our total temperature times P dot P vap for our function of T. And then this will be divided by our total P minus Y. Okay, so that one is actually the same as the last one. And then for our energy balance, this one will be equal to, so FH plus our vapor enthalpy, so HV for V2 and T2. And then we'll go ahead and, is this minus or plus? I believe it'll be plus. Yeah, so plus our liquid enthalpy, so HL for L1 and T1. Then we can go ahead and do our vapor enthalpy again. However, this one will be for V and T. Okay, so I believe it's the same for the most part so far. And then we'll go ahead and again do our liquid enthalpy, so HL, and then this one again for L and T, and then go ahead. I think we need another one here, and then divide this by our feed H. Yeah, that looks good. Okay, so again, go ahead and return this. We're going to be returning the exact same thing, okay, as the last one. All right, so now we can go ahead and define our stage N. And this one's going to be a little different because it's going to be just our vec1 and vec. Okay. All right, so we can go ahead and define our T1 and T, and this will be equal to our vector 1 for grabbing -1, and then for our vector grabbing -1. Okay. We then want to initialize our L1 and V1. So I believe it'll be the same as the last one. So we're looking at vector 1. So let's go ahead and grab this one for L1, V1. Let's go ahead and indent it the same. So L1, V1. And then we can go ahead and initialize our L and V. So this will be vec. So let's go ahead and grab this also. Okay. All right, so we have our L and V, and then we can go ahead and grab our X and Y now. So our X and Y. Okay. All right, I'm gonna go ahead and pause this for our the rest of this. Okay, so our mass balance for this one, again, we're gonna have two mass balances. So our first mass balance is gonna be equal to L1 minus our vapor minus our liquid. And again, this is all going to be divided by our feed total. And for our equilibrium, again, we're looking at X times our NRTL gamma function. So P dot NRTL underscore gamma for X and T times our P dot P vap function for as a function of T, again, divided by our total P pressure minus Y. So remember, we initialized that pressure earlier on in the code. So for our second mass balance, we're going to be using our sum function essentially. So JNP dot sum for L1. Yeah, for L1, and then this would be minus our JNP dot sum function for our V. And then we'll go ahead and be subtract this by our bottoms total divided by our feet total. I believe that's right. So GMP dot sum of one minus GMP dot sum V minus our bottom total. Okay. So we're gonna go ahead and return this. So there you go. Our mass balance, equilibrium, and mass balance too. Okay. All right. So, oh, what? Oh, yeah, there you go. Okay. I think that should be good now. Let's go enter that again. Okay, so now we're going to go ahead and initialize our stage functions essentially as a function of our Jacobian. So we're going to be using our jacks, and we initialized it earlier on in our code when we imported our notebooks. Let's go ahead and do that. And it's going to be for uh, three different stages. So stage one underscore jack, and this can be equal to jacks.jit, parentheses jacks dot Jacobian for stage one, and then for 0 and 1. Okay. So let's go ahead and copy and paste this three times. We're looking at three of them. So this will just help speed up the process. So we have our second stage, and then we have stage N, just like we did for our other ones. Stage one, our regular stage, and stage N. Same Jax dot JIT, Jax Jacobian, and then we have to change this. Okay. And then for our second one, we're looking at it from 0 to 1 to 2. And then our third one, again, is just from 0 to 1. So that equates that. So we want to go ahead and define some of our residuals. So this is going to be in a form of ES and CS. We've want to essentially use our zero function for the number of stages essentially in our number of components. So starting with ES, let's go ahead and do ES, CS equals. Okay, so for our first one, this is going to be equal to MP dot zeros, like I mentioned. And then this is going to be for our number of stages. And then what we used earlier, so 2 times number of components plus 1. Okay, and then again, using our zero function, MP dot zeros. And then this one will be for our number of stages minus 1. Yeah, for our 2, and then 2 times our, let's combine this. So number of components plus 1. Yeah, plus 1, and then 2 times number of components plus 1 again. Okay. Oh, okay, that should be good. Let's go ahead and do what we did for the other one. I believe I messed it up. No, 2 parentheses here. Okay, so shift enter that. Okay, so now we want to go ahead and evaluate this now. So this is going to be a pretty large chunk as we have to evaluate our E's as well as our C's, creating some if then, if else functions and for loops. So for first off, go ahead and define, so evaluate ES as a function of our unknown or unc. And then we'll go ahead and I think this will be, yeah, all right, that's fine. Okay, so go ahead and for our liquid and vapor, we're going to be splitting this. So NP dot split as a unc function. And this will be for 0, comma, and then -1, comma 2. Okay. And then we want to do this for our y. So y is equal to our vapor divided by NP dot sum for as a function of our vapor. Okay. And then we want to initialize our ES as a function of 0. So doing this, we're going to equal this to essentially our stage 1 first off. So stage 1 as a function of unc, and then 0, and then unc 1. So unc 1 as a function of our bubble T, our NRLTL function. So NRTL is a function of y and total P. And then this one will grab our zeros here. Okay, I think that's good. Okay, so we want to go ahead and now set our for loop. So for I in range, we're going to be looking at 1, then NS number of stages -1. Okay, I believe this is right, but I don't want to create this if then loop if it's going to be wrong. Good, except we need a colon right here, and then go ahead and shift here. Then we're going to go ahead and create our loop. So we're going to say if I is equal to NF. There you go. So if I is equal to NF, our ES as a function of I, as a function of I is going to be equal to our stage as a function of unc for I -1. And then for unc as a function of just I, as a function of just I. Okay, I believe that's right. And then unc as a function of I plus 1, I plus 1. It's gonna be at 0. So make sure to initialize with a period, comma, and then another 0 period. Okay. Sorry. So and then we're gonna have a else function. So if this doesn't happen, we're gonna have ES I equal to stage unc I -1. So as of now it's the same, I believe. And then comma unc as a function of I, and then unc as a function of I plus 1, and then 0 and 0. Okay, this is okay. So I believe we're pretty much saying here that it's essentially going to be the exact same thing. Um, that this is what's going to happen regardless. I'm going to come back to this. But I believe that's good. Okay. All right. So let's go ahead and come back to this line of code. So we're going to be initializing ES as a function of -1, and we're going to be equaling this to our end stage. So we're going to be using unc again, but however, this is going to be at -2, and then unc at negative as a function of -1. Okay. All right. So we're going to go ahead and return this. So return ES. Okay. I believe that's good. Or we need this here. Okay, there you go. All right, so then we're going to go ahead and define our normal. So essentially, we're still evaluating this based off a norm scale. So norm underscore evaluate ES as a function of our unknown. Okay. And then we're going to go ahead and return this and use our len alg function and p.len alg.norm alg.norm for without ES, then alg. Okay, let me go ahead and shift into this, see if everything's good. I'm gonna pause this and make sure this is right before we move on. So I messed up this first function. I knew that didn't look right, but this is gonna be our F total times our essentially our composition, so Z, and then it'll be our feed H, so feed enthalpy. And shift enter this. I think that looks good now. So we can go ahead and move on. Okay, so we now want to go ahead and first off by setting essentially an iteration, and that's going to be for 25 iterations, essentially 1 to 25. We're going to be normalizing our ESs again, so normalizing our residuals. And then we'll be going ahead and essentially creating an if-then statement. But we also want to create some Jacobians because we're going to be looking at some of our matrices and again using those matrix multipliers that we always use. So let's go ahead and start this. So we're going to say that for, don't like that. Okay, make sure it's still recording. Okay, so we're going to say that for iteration and range for 1 to 25, so 25 iterations, and then put a colon here. We're going to be saying our ESs are going to be evaluated for our unknowns. Okay. Okay. And then we're going to go ahead and essentially normalize our residuals. So norm ES equals norm underscore evaluate ES underscore unknown. And we're also going to want to have to go ahead and print these iterations and normalize residuals. So iter and norm ES. Okay, we want to go ahead and now set up one of our loops. So for if our normalized residuals, so ES is less than 1 times 10 to the negative 8. I don't know why it thinks to give those numbers. It's kind of odd. Okay, so if this is less than 1 times 10 to the negative 8, we're going to break this function. Okay. So we're going to go ahead and go back and start on our Jacobian function. So we're setting these as B and C essentially for our matrices. B and C are going to be equal to stage 1 for our Jacobian essentially. And then we're going to be looking at our unknowns for as a function of 0, unknown as a function of 0, and our unknown as a function of 1. And I'm not closing that yet. And we're also adding our NR. Wow, no. Our NRTL function as a function of our vapor composition and our total pressure, and then as a function of 0 here. Okay. All right, so now we can input another function known as B inverse, so I and V, and then this is going to be equal to our essentially we're going to be linearizing this, so np dot lin alg dot and v, and this is going to be for a function of b. Okay. Oh, okay. All right. So now what we want to do is essentially set our residuals as a function of 0. So starting with our c's, and this will be as a function of 0, and we're going to be using our matrix multipliers here. So b I and V, and then our matrix multiplier, and then C, that kind of function that we just set. Okay, then we're going to go ahead and initialize our residual for E. So this will be at a function of 0 again, and then this will be equal to B inverse matrix multiplier ES as a function of 0. Okay, all right. All right, so we now want to go ahead and set up essentially another for loop. So it's gonna look like this for I in range for 1. So we did this before, number of stages -1. Let's go ahead and put a colon here. And okay, we're gonna be saying that if this is equal to I is equal to NF. Okay, but yeah, we did that up here. Okay, so somewhat similar. However, we're adding another matrices essentially. So B and then C here. And then this is going to be equal to our Jacobian stage essentially. And our unknown is going to be at a function of I minus 1. And then our next unknown function is going to be at a function of, I don't know if this is I. I'll go ahead and pause this. So it's going to be a function of I here, but I, and then our next unknown function is going to be at I plus 1. And then again, what we did in the other part, our F total is going to be multiplied by our mixture along with our enthalpy feed, our feed enthalpy. Okay. So then we're going to go ahead and set up a else function. So our else function, mm, yeah, so else function, don't forget to put a colon here. And then this is going to be for our three matrices essentially. C, and this is going to be equal to our, again, our Jacobian stage. And we're going to be inputting our unknown functions once again. And this is going to be at minus 1, I minus 1, our unknown at I, and then our unknown at I plus 1. However, we're going to be setting these at a function of 0 that we've done before. So again, make sure to put your periods here. Okay, that looks good. Okay, okay. All right, so then we want to go ahead and set up our inverse function. So we're going to initialize this again. So our inverse function is going to be linearized again. However, it's going to be a little bit different this time as we're sending a function of b minus a, and then using our matrix multiply here for our c's as a function of I minus 1. Okay. And then gonna go ahead and set up our C's and E's again. So our residuals here and as a function of I. And then this is gonna be equal to our B inverse multiplied by our C, essentially matrix multiplier by our C. All right, setting up our E's. So E's as a function of I is gonna be equal to our inverse B matrix multiplier here. Let me go ahead and put this in a parentheses. So this is going to be multiplied by our e's as a function of I minus our a as our a matrix multiplier by our es, and then I minus 1 here. So, okay, that looks good. Go ahead and pause this. Okay, so I honestly fixed some indentations. It didn't look all right, so I made them all similar. But moving on from here, we're gonna go ahead and set up our A and B matrices for our end stage. So stage N underscore for our Jacobian, and our unknown here will be -2, right? -2. And then our next unknown is gonna be -1. Go ahead and okay, so unknown 2, unknown -1. And then we're going to set up our inverse again for our linearization. So lin ouch dot inverse. And this is going to be, so b inverse dot equals np dot lin ouch. B inverse dot lin ouch. And then our b is going to be subtracted by our a using a matrix multiplier, cs -1. So I believe it is the same here, except we're using our c's this time. B minus a matrix multiplier, CS. Okay, good. All right, sorry. Let's move on from there. So we're gonna be looking at our e's as a function of -1, and then this is gonna be equal to our B inverse matrix multiplier for our e's as a function of -1. And then this is going to be minus our A matrix multiplier ES as a function of -2. Okay. All right. So, okay. Let's go ahead and set up our deltas. So our delta, first delta unknown, no, delta underscore unknown is going to be equal to np dot zeros. Okay, let me go ahead and brush up on this part a little bit. Okay, so we will be using our zeros function here, and then this will be our zeros like function for unknown, unknown. Okay, and then we'll go ahead and set up another delta unknown, essentially just our change of unknown at a function of -1. And again, we're still solving for our e's here. So that is a function of -1. And then go ahead and set a loop. So we're going to say that for I in range, our n's, so number of stages, ns, minus 2, and then ns -2, and then -1 and -1. Okay, and let's go ahead and put a colon here. And I'm going to say that our delta underscore unknown as a function of I, as a function of I, is going to be equal to our e's as a function of I minus our c's as a function of I. And then at our matrix multiplier for delta underscore unknown for our I plus 1. Okay. Oh, no, no, no. Ah, what happened here? ES. Two-plate index out of range. Hmm. I did not want to shift enter this because I wanted to just finish it out. Let's go ahead and see what kind of mistake we made. I'm gonna be back. Okay, so I just keep forgetting to shift enter on my code and I wasn't initializing some things and I fixed some indentation issues, but I shift enter on this and it came out with this, but I know we're not there yet. We still have some things to do a part of this, which essentially we're creating a bracket. So for lambda of t and then normalizing our residuals again, eval es for our unc plus t yeah plus t times delta underscore unc, and then this will be for our, oh man, blanking out here. Yeah, so this is for xa and xb. So xa is going to be equal to 0, and then our xb is going to be equal to 1. Lambda. There you go. Okay. Go ahead and set up our t, which we're going to minimize scalar function. And this is going to be for the t, normalizing our residuals again. And then our unc plus t. Yeah, unc plus t times delta underscore unknown. And then our bracket for nothing on the left, right? And then 3 dot x. Okay. And go ahead up and set up our new unknown, which is unc plus t times delta underscore unknown. And let's go ahead and do this. All right, while this is loading, I'm gonna go ahead and pause it just to, see if this is correct. All right, perfect. So that's good. Which is this is essentially our iterations for all of our normalized residuals, 5 of them at least. So we can go ahead and do something else here. We can go ahead and get all of our unknowns. Essentially, this is an array of all of our unknowns. So something we can look at. Um, let's go ahead and extract. We want to go ahead and extract our essentially our liquid and vapors. So L and V is going to be equal to MP dot split for our unknown from this, and then our -1 again. Okay. And then this will be 2. And then we can go ahead and set up our axis again. So axis is going to be, we can set up our axis here at least, since axis is going to be equal to 1. We can then go ahead and set our x's and y's. So our x is going to be equal to L divided by MP dot sum for L and axis is also going to be equal to 1 here. Yep, our axis is going to be equal to 1, and we can go ahead and set up another bracket here, and then our second one's just going to be none. All right, for our y, it's going to be equal to our vapor divided by mp dot sum. For our vapor again here, and our axis is going to be equal to 1. And then again, it's going to be set at none. Okay. So we can go ahead and set up our x and y essentially together, which our x's is going to be at a function of 0 here, and then our y is going to be at a function of 0 here, or colon, so colon, comma, 0. So empty, empty, comma, 0. Okay. All right. Okay, so let's go ahead and set our operating lines now. And this is essentially going to be defined by OPX, so operating line for our X and then operating line for our Y. Our first one is going to be using our MP.R function, and then our Y is going to be set at a function of 0. And then we're going to be using our repeat function for these X values essentially. And it's going to be for X at -1 here, and then we can go ahead and put a comma 2 and end that one, and then our next x is going to be a function of -1. Okay. All right, so for our y's, this is again going to be equal to our np.r function, and we're going to be using our np.repeat, I believe. Okay, so I believe we add this to our y2 here. Yeah, it assumed we're not adding that together. Go ahead and pause this. Yeah, so this does not need to be here. Let's try that again. Okay, so we're almost done. We finally got our operating lines down. So we're just gonna go ahead and honestly just set up our function. This is gonna look similar to some of the old homeworks that we've done. So we're gonna be setting our new total pressure equal to 101,325, as we've seen before. Our x1s are going to be equal to, we're going to be using our mp dot length space function, and it's going to be from 0 to 1 to 101. And then we can go ahead and create empty arrays for first off our t's, and then empty array for our y's. Okay, and then we can go ahead and set another for loop here. So if x is in our x1s, think we need that here. Our T, so our total, our temperature here, and then our Y. Oh man. Go ahead and pause this again. So, right, forgot to put a colon here, and then Y1 and Y2. And then this will be equal to our bubble T, our NRTL bubble T. And we're going to be creating an array for, first off, our X's, and then our Y's, which is essentially just 1 minus X1. And then we can have this X1 here. There you go. And then our total pressure here. And then we can go ahead and append, first off, our T's. So append our T. And then go ahead and append our Y's, right? We set an empty array for them. So append Y's, append, and then Y1. Okay. All right, so I think that looks good. All right, so we're pretty much done here. We're gonna go ahead and just make our subplots. So fig equals make underscore subplots, and then add a scatter. So fig dot add underscore scatter. Our x is going to be equal to our x1s, and our y is going to be equal to our y1s. Okay, add another scatter. So fig dot add underscore scatter. Our x is going to be equal to OPX, and our y is going to be equal to OPY. Yeah, okay. All right, so last thing, we're going to update the layout for this. Big dot update underscore layout. We're going to set our width equal to 600 and our height equal to 600 and our template equal to cloudy underscore dark. Okay. No, that is not what we want to see. The stair step is right, but something is definitely off here. I'm gonna go back and see what kind of mistake I made. Okay, so I made a mistake here, so I'm gonna go ahead and put this back. And then let's see. Pretty sure that's our mistake here. All right, and perfect. So essentially this is our stair step right here. Let's go ahead and read this. We have our XY diagram with our equilibrium curve. Yep. We have our liquid vapor liquid composition to add in between trays. So yeah, that's perfect. This is exactly what we want to see. We did everything here. We applied our code towards the solution of a distillation column. Equimolar ethanol water mixture for assume that they're in saturated liquid temperature, and we implemented this mesh equation in the code. Yep, we did all this, applied our Thomas algorithm as well as our Newton's method. Yep, as well as the linearized np.lin al try diagonal block equations. So at all of our iterations, yeah, this is perfect. And yeah, that completes this video, and which is my last video. Thank you, Carlos, for everything.